Hello, welcome to video 50 in the lecture Advanced Mathematic Modeling. So in the last video we reflected a little bit how do we do measurements of physical objects, and we've seen we need scales and we need to make coverage of this object, coverings of this object with the scales, and then we need to count. Basically that's the measurement. We need to measure how many objects do we need to cover how many scales do we need to cover our object, and but then we give this in units of our scale to the dimension. So that was how we make measurements, and here the dimension somehow is hidden inside this, and this gave us the idea to how to measure the dimension. We just measure a volume at different scales, and from this we get a formula how we can extract the dimension. Of course, now we have the problem of this, it's only approximate, because we have always measurement errors, because our scales will never totally perfectly fit our objects. And if you measure only at 2 scales, that's not enough. So we would like to measure at systematically at very, very different scales. But then how could we relate these formulae? I mean, this kind of fractions, and now we can solve this for d. We can only do if we measure this at 2 different scales. But let's say if I would have this measured at 10 different scales, how could we how could we extract the whole thing? And here now, think in our lecture, when you look at this, you see, hey, that's a power law. I mean, the volume goes with epsilon to dimension, and we know how to extract the critical exponent of a power law. The dimension is a critical exponent of the power law. Okay, maybe let's write this down. If we have this formula, n equals v, volume equals n, and we should write n, which depends on our scale, times epsilon to dimension d. So this is a power law. And then our dimension d is just the critical exponent. And now we have the relation to the previous parts of our lecture when we looked at power laws and scaling. Now we see, okay, a dimension is just a critical exponent. And now we know how to extract such a the exponent from a power law. We need to make a plot. And maybe we should have written this also a bit differently, because this volume is a constant, and maybe actually the power law we are interested is not this power law, but it would be the power law is n of epsilon. This equals the volume times epsilon to minus d. And then you see, because this is now the power law, what in the form which actually interests us, because here we have our n of epsilon, and here we have our scale, and we see now we have a power law again in the usual form, that we have this minus critical exponent is negative, and so now we can measure our volume at different scales. But also from our discussion, we always want to look this in a double logarithmic plot. So actually here we want to have logarithm of epsilon. Here we want to have the logarithm of n of epsilon. So we make the measurements at scales which are equally spaced on a logarithmic axis. And then if we measure our object at these different scales, then this should be a straight line. And then the critical exponent is obtained if we take the slope. And now we also know how we can deal with these imprecisions, because if our scale is very large, maybe take here this example that we had here, when the scale is very large, then we make a big error because the scale doesn't fit into the line. Now if we make our scale smaller and smaller, so this what's over our object is always less, or you can say our object is better fitted, or maybe you can see it better in the two-dimensional. So we make here a mistake because we cover too much. But if we would take smaller rectangles, smaller scales, we would have a better fit. So actually what we expect is, if we have here large scales, we have some errors. So that would be actual measurements. But when we go to smaller and smaller scales, maybe you could also make here measurement error bars in. Yeah. So the error bars would get very small. And so we have to look for our curve in the limit. So d is obtained as the slope of a double logarithmic plot. But in the limit of epsilon goes to 0, we have to go to very small scales so that these measurement errors are not too big. And then we can measure at many different scales, not only as before at 2 scales. We measure with many scales, we look at the slope, we see how does our n increase when we reduce the scale, and this gives us a power law. So the concept of a dimension is related to a power law and a critical exponent. We can also try to, if we have this equation, try to solve this equation for the exponent d. So we get an alternative way how we could solve this for the dimension. So, and we again take the idea to take the log. So we log this equation. Then we have log of our n. Maybe I here write it n epsilon. It's a bit shorter like this, log n epsilon. So this equals the logarithm of our volume. And now I want to have a positive d, so I can do this by taking this is 1 over epsilon 2 power d. Then I take the log, then I have d times log of 1 over epsilon, so I have a positive sign here. And now you see when we need the limit epsilon goes to 0, then this n goes to a very large value, and log of 1 over epsilon goes also to a very large value. And so we can forget then the log of v compared to the others. So log of n epsilon is approximately d times log of n epsilon is approximately d, the dimension, times log over 1 over epsilon. And then we get a formula for the dimension. The dimension is given as the logarithm of the number of scales I need divided by the logarithm of 1 over epsilon. And actually I forgot to write down the limit, limes. In the limes, epsilon goes to 0, and actually this limit should be here. I mean, usually we write this limit before, but I just forgot to write it. Yeah. So we can also get the dimension if we take the limit epsilon goes to 0 of this fraction, the logarithm of the number of objects divided by the logarithm of 1 over the objects. And because like this log v term gets more and more unimportant the smaller we get here. So that's a formula we will maybe need later to calculate the dimension of an object. And maybe it's also clear when we think a little bit about this, we can only in the limes, so maybe you write this down, measurement of dimension. So we need to go to limes of very small scales. But then it's clear we can go only so and so far in very small scales, because let's say you take you want to measure an object like a stone or something, and now you go to smaller and smaller scales, and then suddenly the granular structure of the material becomes important. Let's say you have an object. We want now to measure the dimension of this. So we need to have small scales which are small compared to the size of the whole object. That's kind of clear. So the small boxes must be very small. But when you zoom in, if you zoom in or zoom out a part here of our stone, then we will see here the granular structure. So actually, so the stone is built through, from you know what I mean with this. So like if we look with a magnifying lens here to a small piece of some material, you see some coarse structure, and even if you go even smaller, you would see molecular structure. And then things suddenly looks very rough again, and there are holes, and so this means if we make the same plot here again, here we have log of epsilon, and we have the log of n of epsilon, and so we should expect there to be a scaling regime where our measurements would be here perfect, and then okay, we would start to see error bars. So it would be hard, and maybe we would get even some deviation. This is strong error bars when our scale is too big for our object. But then there is a certain minimal scale, and if we go to scale smaller than this, it's a question mark. We don't know what's happening here, because suddenly our object is not a uniform object anymore. We have some roughness structure in there, and so we expect such scaling only in a certain range. As always with power laws, we said scaling will always only be in a certain range. And even though in the mathematic theory we need to go to the limit epsilon goes to 0, in practice there's always, from physical constraints, a minimal epsilon where we can go to. And now the question is, for example, what would we get if we measure natural objects? What do we obtain when measuring natural objects? And then you would say, why? I mean, we measure here a straight line, and the slope gives the dimension. So what's the question? But you know, I mean, if we have a slope, why should the slope be a natural number? Then you can think about. I mean, now we now derive this concept how to measure the dimension. It's the slope, and we know the slope could be a real valued number. And now this is related to the question, take for example a sponge. As an example. So when you look at a sponge from a large distance, so it's like a typical sponge, you need to clean the blackboard. Yeah? It looks like a three-dimensional object. But if you now zoom out the structure at a smaller scale of the sponge, then you see, I mean, I don't know how to paint it. Let me try to do this. I mean, so you will see holes in the sponge. So you will see holes, big holes. You will have smaller holes, these holes, and then so here it's a bit deeper. And then you have here the material of the sponge, and then you see it's an object which has a lot of holes. And when you zoom in the surfaces of these holes, there seem to be like two-dimensional interfaces. If you look into this, and so like this holes could be like here this lengthy things, and it's like you have like at smaller scales it looks maybe a little bit like a two-dimensional thing which is intertwined in itself. So actually, what then is the dimension of such an object? Yeah? Is this rather a three-dimensional object? Or if you look at the microscopic structure, is this maybe an object which is set together from two-dimensional from 2D manifolds? And now we could answer these questions. For example, if we take smaller pieces of the sponge and just measure the weight of the sponge, and would measure how would the weight of a sponge scale as the typical size of a piece of sponge, and then we measure the exponent and could see, is this now 2 or 3? And in the next, so like suddenly you see when we look at this a bit more serious and don't have an abstract physical space like just our room in which we are in, but if we take natural objects like a stone which is set together of small molecular pieces, or a sponge which has actually a very complex geometry, if we look a little bit, if we zoom a little bit in, then you see suddenly the question of the dimension of such an object is not so trivial anymore. And we in the next video we see how this was historically found for the first time. For the moment, thank you.